what I'm sketching here in one curve, this curve I'm sketching down here is a 2 times sine 70. It's not, it doesn't have 3 times sine 5t. So this one have frequency 7 over 2 pi and amplitude 2, and that's the curve. And this frequency is a smaller frequency, then so I'm going to change to that curve now. So you can see that curve is a different shape, and a larger amplitude and a smaller frequency. And I call this, each of this thing, pure wave. That looks like this. We have amplitude and a very well defined period and frequency like that, and the other one is also pure wave. If this two pure waves juxtaposed, just like if it is acting like a force, and it makes sense is adding these two together. And what's going to happen when you put these two things together is sometimes a lot more complicated than we think. So here is the curve when you put these two waves together, right? And you can ask this opposite question, that if we are observing this wave in the nature, and how we're going to actually decompose it into two pieces. And mathematical theory says that there's no two ways to do that. There's only one way to do this. So if somebody tries using some ingenious method to decompose it into sum of two pure waves, and the other person does it in a different method, they're supposed to end up at exactly the same answer. So there's a unique way to decompose any periodic phenomenon to sum of the pure waves. So that's one thing that we're going to experience. And if it is really complicated, of course, what pure waves that is involved in this is really complicated. We're going to look at a simple thing that we can handle using addition and subtraction formula. Okay? So the first one they have is this example. Write the sum of these two waves is 3 times sine x plus 4 times cosine x, like this. So it seems like a pure wave. Whatever that x is, it could be 7t, whatever, that we just don't touch that whole piece, just leave it there. And the other wave has exactly the same frequency. Maybe x is at same 7t, but it has a slightly different amplitude and slightly different curve. If you put these two curves together, and what's going to happen? If the frequency part is the same and sine and cosine it changes like this, it's possible to rewrite this one into the following form. It says k times the sine of x, then nothing happens to that x part, and plus some additional number kick in. This phi is determined by this 3 and 4. They're claiming you can write this sum of two waves into a compact form like this. Constant k, not depending on x, and constant phi, not depending on x. You can write it like this. So it's not like something complicated. It becomes another pure wave, right? And what is the phi doing to the pure wave? It's horizontal shift. Okay? So if you add these two curves that have different amplitude, nothing funny happens. It just becomes another simple pure wave that is shifted a little bit. All right? Well, it's not easy to discover something like that. If you have time and play with it because you're interested in this kind of thing, it is something that you're going to probably discover. But at this point, within 1 minute, of course, it's unreasonable to discover this answer. We just have to simply learn how this one goes. So here's the idea. If they figured out how to rewrite this sum of two pure sum into that shape, you look at the answer and realize you can use the addition formula here, right? X plus phi. So I'm going to reorganize this one into addition formula. So it's like this. Instead of writing like this, sine x times 3. So sine x whole quantity times 3. I wrote the 3 later. And plus cosine x there times 4, like that. If you write it like this, I hope you recognize it's more closer to the addition formula form. Here's a sine x. Maybe we can realize this one is a cosine of phi, just like in the addition formula. How about this one? What is it supposed to be then? 4? Sine phi, right? If I can match that 3 and 4, using this cosine phi and sine phi, that becomes addition formula, don't you think? Sine x times cosine phi, cosine x times sine phi. Then using the addition formula, this becomes a lot simpler form. All right, who remembers about the values of a cosine phi? Is the x-coordinate of unicircle, right? So it's only in between 1 and -1. There's no chance you're going to meet this 3, right? And sine phi is not going to be 4. It's not possible to match that. So here's a further idea. Although we can't reach that 3 and 4 using the unicircle, we can make the circle bigger and hit that 3, 4. Does the idea make sense? And then once you hit that 3, 4, there will be sine and cosine kicking in because it's on some circle. So here's the idea. Let's not match this one and cosine because it doesn't work, right? Cosine and sine are very small value. Why don't we make that one x-coordinate? Why don't we make that one y-coordinate and hit the unicircle? Not the unicircle, some circle that hits it. So here is the circle. Here's a 3, 4. Maybe more of that size, 3, 4. I don't know where I stopped recording, but it's just there. Sine of x plus phi. Thank you. That's it. All right? So I kind of explained why that sum of two pure wave become into this compact form there, right? And the 5 popped out. Remember how we got the 5? 5 came from here. The x-coordinate and y-coordinate is a square, and that's how I got it. Square root of x-coordinate and y-coordinate. All right. So in exact form, this is all we're going to get. But if you have to figure out what this phi is, since we're staring at it here, we can actually approximately calculate, right? So once you plot this point like this, to me, the best way to calculate phi is computing the tangent phi. So what is the tangent phi here? 4/3, y-coordinate divided by x-coordinate. Is that right? And I don't want you to go and conclude that phi is a tangent inverse. Just first calculate tangent inverse of 4/3. Can somebody calculate the approximate value of this one, please? 4/3, I think is 0.9. There was a question going from this to that. There is no mechanical method of going from here to there. It is the sine formula. You will recognize it. Does that make sense? Yes, right. Right. So there's no factorization or manipulation. It is just a formula, right, going backwards. All right. So I calculated to do a little bit more about the information, to give you more information about this phi. I'm calculating approximately. For that, I calculate tangent phi equals 4/3, and tangent inverse is 0.9279. And the question is that, is this one really this phi value? How do you know that? Anytime your angle is the first and the fourth quadrant, you do the tangent inverse, that is the angle. But if I change the sign in here, your point maybe is over here, maybe over there, then whatever you get from tangent inverse is not really the angle. Think about the situation that tangent phi was -4 divided by -3. Isn't that the same thing, 4 divided by 3? But where is that point? This point is opposite side, third quadrant. So calculator will give you only this angle, but if you want to get to the other side, -4, -4, -3, what should we do to get to the other side? From the tangent inverse, you have to add 180 degrees to get to the other side, right? Which is pi radian. Here you don't have to, because it's already in the first quadrant. So what is phi here? Phi is 0.92, approximately 0.9279. Okay? So let me write down this answer in here. We can't do this exactly, But I explained that it can be put into this form for this phi that is right there, but approximately the 3 times the sine x plus 4 times the cosine x is approximately 5 times the sine of x plus 0.9279. If you sketch this one using the calculator, if you sketch this curve using the calculator, you can see their pictures are identical. Very, very small difference if you overlap it because we use approximation. So addition formula allows you to sum of these two pure waves to appear in a compact shape like that. Do you have a question? So here's the exercise. Write, let's say, negative 2 times the sine x plus 3 times the cosine x in the form of k times the sine x plus phi, where k and phi are not depending on x, is a completely determined constant. Just change the problem from positive 3 to negative 3 in here. Was that alright? Any question? Yeah, we definitely need to explain a little bit about this tangent phi business. So I sketched the point down here because that's the coefficient you see in the original formula, so I applied it there. But when you calculate tangent phi, you really calculate 3 over 2. Calculator doesn't know what you plug in there is really negative 3 over negative 2 or 3 over 2. That's the same number when you simplify it. So it gives the angle 0.9827 radian, but you know that's the first angle in the first. It's the same as 2 comma 3 over here. That's the angle it gave you. But you want opposite side of the angle, so you have to add 180. In radian is pi. So this time you have to add pi, and 4.1243 is the correct phi value. Does that make sense? Yes. Right, that is a correct concept, but I still like this numerical value better because that makes students show more about how they understand these things. But what you just said is correct. If you just write a tangent inverse or whatever plus pi in that's exactly the correct thing. Definitely things to do if you forgot to bring a calculator in the test, and that's the way to go. All right, any other questions? Does that make sense? Yeah. What is the meaning of this calculation? Is that if you add these two pure waves with the same frequency, and there is a way to put it into a compact form. Okay. Usually we're more interested in, here's some compact form of trigonometric functions. Can we write it as a sum of a pure wave? That's the more interesting part. But it kind of helps us understand this problem. Okay? So here is the bonus problem. I have a YouTube video for this one, so you can watch that too, but so that I might go a little bit fast on this one. But if you do this one, you get a bonus point.